Good afternoon. We're here to start the session on technologies to transform the energy system. And so welcome. It's great to see you all here. I'm Sally Benson. I am a professor of energy resources engineering at Stanford University. I am also the director of our energy institute called the Precourt Institute for Energy, and also the director of the Global Climate and Energy Project, which is a project that's been going on about 12 years focused on energy systems innovation. So the plan for today's session is as follows. First, I will give a general introduction to what I call game-changing energy technologies. And I'll talk about energy technologies that are here now, energy technologies that are coming soon, meaning in the next 5 to 10 years, and then energy technologies that are on the horizon. Those are things in the longer term that we're going to need to continue to drive down the energy intensity and carbon intensity of our energy system. After I do that, we will have two other talks. And I know from all of the discussions so far at the conference that both of these will be of great interest. The first of these will be by Gardner Hill, who is the Director of Carbon Solutions at BP. He's been working on carbon capture and storage for more than 15 years, and BP was one of the really early entrants into this technology. So he'll be sharing his experiences on CCS. And second, we have a very important topic, and that is of energy systems integration. As technologies for low-carbon electricity generation in our portfolio mature, we're finding the challenge is not having cost-effective generation, but how to integrate these new resources into the existing electricity system, because it represents a fundamentally different paradigm for how to operate the grid. So Professor Mark O'Malley from the University of Dublin will talk about the very, very important issue of energy systems integration. He is also the leader of a new institute on energy systems integration and international collaboration focusing on that topic. So I would like to invite our two speakers to join us on stage, and then we'll get on with the program. We will also have the opportunity for questions at the end, so each of our talks will cover about 20 to 25 minutes, and then we'll open it up to questions from you. All right, with that, I will start the first talk, so if I could have my presentation up there, that will be great. And I'm going to be talking about game-changing energy technologies for a sustainable energy future. To begin this, I'd like to provide the context that by 2100, that we will have between 9 and 10 billion people on the planet. And it's reasonable to assume that at that steady state, we may need, under a business-as-usual kind of scenario, about 2 times the global energy supply. And the challenge is how do we provide this energy supply while at the same time protecting the environment, sustaining healthy ecosystems, having clean air, clean water, and a stable climate? How do we do this while providing energy access to those in need? How do we do this while maintaining economic stability and in such a way that it protects national security? So this indeed is quite a challenge. And in the previous session, if you were here, you heard some interesting statistics about the terms energy intensity and carbon intensity. And what I show you here is I like to say, sort of a magic formula for achieving the 4 goals that I described, allowing GDP growth, providing energy access to those in need, reducing impacts to climate so that we can sustain a lower than 2 degrees C target, and also preserve national security. So the formula is this. It says REI plus RCI has to be less than minus 5.5% a year. So what this means is that the rate of change of the energy intensity plus the rate of change of the carbon intensity needs to be less than minus 5.5% a year. So to put this into context, we can think today that the energy intensity has been improving at a rate of about 1% a year for quite a long time. And also, as you saw, if you look over the past several decades, that the carbon intensity, though it's been moving up and down, in fact, if you look over that entire period, the carbon intensity hasn't changed really at all. So we need to fundamentally go from an energy system that's been improving at a rate of about -1% per year in terms of these metrics to about 5.5%. So that's obviously quite a challenge. So not only do we need to do this, which represents a significant change from the current situation, but we have very little time. And we have to do this quickly, and most importantly, we need to begin doing this now, because every year we wait, that carbon bank account, the amount of carbon in the atmosphere that we can tolerate before we are committed to more than 2 degrees C, every year we're chipping away at that. So the keys to achieving these 4 goals in our energy system are as follows. First, we need to decrease reliance on depletable energy resources. Second, we need to increase the utilization of local resources, improving energy security. We need to radically reduce the energy intensity. We need to radically reduce the carbon intensity. We need to improve reliability and particularly flexibility as we begin to introduce these sources. And we need energy technologies that can be deployed at enormous scale at very low cost in order for them to be competitive with the energy system that we have today. So I'm going to devote the rest of my time to energy game changers. So what do we mean by energy game changers? Well, these are technologies that can shift the paradigm from our current situation today of large central generation, primarily from fossil fuel resources, to a much broader portfolio of energy solutions with low carbon intensity. And I'm going to divide my remarks into 3 areas, game changers that are here now. And these game changers that are here now are a reflection of the tremendous success of the R&D investments, many cases beginning in the 1970s, and then the industry beginning to scale up these technologies and begin to scale these so that they're starting to really make a difference in our energy system. Next, I'll talk about the category of energy technologies that are coming soon. So these are technologies that we can expect in the next 5 to 10 years will start to have a significant impact on our ability to reduce energy intensity and to reduce carbon intensity. And then finally, I'll talk about solutions that are on the horizon. So these are things that really aren't ready yet. There might be pilot projects. They might be in somebody's research laboratory at a university. But nevertheless, they show promise. And if they were to be successful, they would provide game-changing opportunities in the energy sector. So I'll begin first by a discussion of the game changers here now. And I think that this has been nothing less than a remarkable decade of innovation in the energy system. And many of us, I know, sort of live this and breathe this every day, and sometimes it's hard to see that there's been so much change and so much progress. But the 3 technologies that I would like to highlight are wind turbines, photovoltaics, and natural gas. So looking first to wind, we see the graph on the right here. This is the amount of installed capacity for wind globally. And we've had about a 25% year-over-year growth sustained throughout this entire period. This growth has come in part from technological innovations, such as larger blade size, improved generators, better manufacturing, better power management on the wind turbines themselves, and then even moving on to wind farm optimization so that you don't just optimize a single turbine, but you optimize the whole facility. And of course, the benefits of this are it's a large and distributed resource. It's basically no emission electricity generation. It doesn't use water. And today, about 3% of global electricity comes from wind today. Now, if you look back a decade ago, I would argue that nobody would have predicted this would have happened. And there's every belief that, that this will continue to grow and expand as we move forward. The second technology I want to highlight is photovoltaics. Again, looking to the chart on the right, we see enormous growth, averaging year over year about 45% annual growth rate. That's extraordinary to sustain this. And if we look at the key innovations here, clearly efficiency improvements on the cells and modules themselves, and also significant improvement in the manufacturing, driven largely by the investment made by the Chinese to scale up the technology, to develop the appropriate supply chain, and so forth. And of course, here the benefits are that we have an enormous and widely distributed resource. It can be used for both distributed generation, off-grid generation, and even utility-scale applications. And again, it provides electricity with no emissions during the operational phase. So looking a little more deeply at the reason for this tremendous progress in photovoltaics, I'd like to draw your attention to this chart. You don't need to pay attention to any of the details, but this is a chart chronicling the technological improvements in photovoltaics beginning in the 1970s. And back in the 1970s, there were about 5 technologies for generating electricity from sunlight. If you look today, it's nearly 3 times that, so many other technological platforms for doing this, material systems. And then very importantly, you'll see that all those curves continue to improve. The efficiency of those cells improves over time. And not only are we seeing this tremendous improvement, but we have some really exciting new entrants into the photovoltaic fields, in particular a material called perovskite, which has gone in a period of about 3 years from an efficiency of about 5 or 6% to now cells with nearly 20% efficiency. So there's an enormous investment by research universities and companies alike continuing to improve this technology, which gives me lots of optimism that it's going to continue to improve. But of course, it takes more than efficiency improvements. We really need to drive down costs. And again, this chart, sometimes called Swanson's law or Swanson's chart, is basically a learning curve for photovoltaics. And if you look back into the 1970s when these devices were first being manufactured, they were hundreds of dollars per watt peak. If we look today, they're about 60 cents you can buy these systems. And if we just look back a decade ago, it was about $3 a watt peak. So a 5-fold improvement in such a short time. And there have been many analyses which suggest that these kind of improvements, that there's lots more in the pipeline, and we can expect that costs will continue to drop down. So this is an example of the real benefits of a technology that is here now, continuing to improve, and that we can expect will have a huge impact on the electricity system of the future. The third game changer that I'd like to talk about that's here now, primarily in the United States, but there's no particular reason why it's limited there, is shale gas. So if you look to the chart on the right, the paradigm in the United States was that natural gas production was going to continue to decline, that we were building LNG terminals expecting to have to import natural gas for the applications in the industrial power and power sector and for domestic heating and cooking and so forth. But instead, some very persistent people took existing technologies, horizontal drilling, hydraulic fracturing, and they combined them in such a way that it made it possible to extract natural gas from rocks that would otherwise have been thought of as unproducible. But that wasn't all they did. To make this really economical, you need to have a supply chain and logistical management par excellence. And in fact, that's what's been done. So the benefits in the United States that have been realized is we have very low-cost electricity generation. As a matter of fact, it's the lowest cost option around, and the real effect has been to result in the shutdown of the operation of a number of coal plants across the United States, so much so that actually our emissions have declined. It also is excellent in that it provides flexible power generation, unlike a coal plant or a nuclear plant, which is hard to ramp up and down, that a natural gas plant can basically match or complement the profile of renewable energy resources, making it easier to increase penetration of those. It's much more efficient for generating electricity than coal, depending upon how you're using it, 20 to 50% more efficient, and it's got about half the CO2 emissions and much fewer of the particulate emissions, so you have significantly reduced air pollution. And again, in the United States, this has resulted in very low-cost natural gas. So again, a technology that no one would have expected 10 years to be on the scene, but already making major impacts, not only in reducing emissions from fossil fuel use, but also opening up more opportunities for renewables. So the key to all of these things, how did it get to be a really game changer? Okay, so you need to get into this virtuous feedback loop, which is really critical success. You need to get in a situation where you do more, which drives down the cost, so it costs less, and if it costs less, you can do more. And once you can establish this cycle, once the industry begins to scale, that you can have rapid penetration of these new technologies. And in fact, all of these game changers have followed exactly this cycle. So now I'd like to move on to game changers that are coming soon. And there are three that I would like to highlight. And I recall coming soon means technologies that will be available in the 5 to 10 year time frame and begin scaling the way I showed you that those other three technologies have. And the first one is what I call the confluence of information technology and energy technology, or perhaps more broadly, energy systems integration. And Professor Mark O'Malley is going to be talking about that quite a bit more, so I'll just say very little about that. The second one is electric cars. Here's a picture of a beautiful Tesla car. They have made real inroads in making electric cars not something that you do because it's good for the environment, but it's something that you do if you want to drive the highest performance car with the lowest environmental impact. And then the third area is grid-scale energy storage. As we continue to add more and more renewable energy onto the grid, energy storage is going to become progressively more important. So I'll say a little bit about each of these. So I'm going to do this by way of example. And one of the things that we've been working on at Stanford, as is Professor Ram Rajagopal, is that he wanted to look at demand-side management. So in the future, we expect that customers will also participate in energy systems integration, that the customers can modulate their need for electricity depending upon availability of that, expressed either through a price signal or something else. And California has been working on demand-side management, and in particular, they had a certain vision of what the typical customer was like, and so they designed an incentive program around those kind of customers. Well, it turns out if you actually dig deep into the data, and this was over 1 million records of consumers, that what they actually found is that the individual consumers did not behave at all like the typical average California profile. So what they've been able to do now, by the availability of this information, they've been able to categorize people not into one type of profile, but about 25 different kinds of user profiles. And so now the utility company can target demand-side management programs or energy efficiency programs, particularly to those users who could benefit most and who could provide the greatest value back to the electric grid. So that's just one example of the kind of technologies that are coming soon, and you'll hear much more about that from Mark O'Malley. So battery electric vehicles, there are really a couple of things that are important. One, the battery has to be low enough cost. And second, it has to have a high enough energy density so that you can drive kind of the equivalent of you can drive on a typical gasoline car. So those are the two parameters. And if we look at, say, last year or so, each of those needed to be improved by about a factor of 3 in order to make battery electric vehicles really competitive. And this is a chart, highly relevant chart, showing the performance of batteries. This is from a paper in Nature Climate Change. And again, dramatically documenting the cost reductions that have occurred over the past few years. And it's been disaggregated into sort of the general market conditions, and then that bar on the green are the market leaders. So these are the people with Tesla and the Nissan Leaf who are really driving battery performance. And that apricot-colored bar, once we're there, $150 a kilowatt hour, battery electric vehicles, in fact, will be competitive with traditional internal combustion cars. And as you can see, this is coming soon, and there's very good reason to believe that we are getting to be on this virtuous cycle of doing more and lowering costs. And then finally, the issue of electricity storage for the grid. So often today, people are using lead-acid batteries to couple with photovoltaics, for example. Turns out this really isn't a very good idea. And batteries are lead-acid batteries are very energy intensive to make. As a matter of fact, if you look at all the energy it takes to build a battery and then you figure out how much it can deliver over its lifetime, it's only a ratio of about 2 to 1, meaning you only get 2 times more energy out of that battery than it took you to build it. So we need other kinds of batteries. And this is just one of the many solutions, but Tesla will now be offering home battery systems that, at least in California, for certain customers could be cost competitive. And particularly for those people wanting to move off the grid, this is a technology, though still quite expensive, is coming soon. So I'd like to move on to the last section, and these are game changers that are on the horizon, meaning they really aren't here yet. They're either too expensive or we haven't perfected the material systems to make them work. And there are 3 of them I'd like to highlight. One of them is carbon dioxide capture and storage, and you're going to be hearing from Gardner Hill more about this, so I'll say very little. The second area is something that sometimes is called CO2 reuse. I like to call it abiotic renewable fuels. The idea is that you take renewable energy, and if you have the appropriate catalyst, you can convert carbon dioxide and water into a fuel that can be used then in the transportation sector or is simply a way of storing energy. And then the final one is perhaps one that you haven't heard of, which is passive radiative cooling. So these are my 3 on the horizon. There are many more opportunities on the horizon. These are 3 that my research program focuses on very heavily. So moving on to the first of these. Whoops, I'm not seeing a change. There we go. Okay, so CCS, is it here now? Is it coming soon? Is it on the horizon? Well, I think the really good news is that we actually have our first full-scale power plant with carbon dioxide capture and storage. It's the Boundary Dam project in Saskatchewan, Canada. This was a critical project to develop because we really need to get cost and performance data on this technology. We know how to capture CO2, we know how to store it, but integrating that with electricity generation has been a formidable challenge. So we are now beginning to get experiences with that. And again, Gardner will talk a lot more about that. This is the little circle there is actually the capture unit on that facility. Okay, so just to say a little bit more about the broad vision for abiotic renewable fuel. So abiotic meaning we're not using plants. So this isn't corn, this isn't cellulose. Literally we're taking carbon dioxide, ideally carbon dioxide captured from large stationary sources such as power plants or cement plants or steel factories. And we take sunlight or wind. We have our input streams of carbon dioxide and water. We have a variety of processes, catalysts that can actually make alcohols, for instance, with these. And the idea is we could take these products and make a variety of fuels or chemicals or operate chemical processes with them, which will provide what we'll eventually need as an alternative for transportation fuels. And then finally, just saying a little bit about passive radiative cooling. So we all know that we can get energy from the sun. The sun radiates on the surface of the earth. We can capture those photons, and we can use those to generate electricity. But there's another resource that we don't often think about, and that resource is the cold resource of the universe, which is about 3 degrees Kelvin. And the Earth is about 300 degrees Kelvin. And so now the Earth is radiating out into space. And it turns out, right in the radiation window of the planet, there's actually a part of the spectrum where we can radiate energy out into space very, very efficiently if we have the right material systems. And so what happens when we're radiating out into space, we're actually cooling our system. So here's a little example of some work from Shanhui Fan at Stanford University. It's a little mock-up of a system. It's basically got a radiative cooler, which in this case just consists of silicon dioxide on top of aluminum. You put it out at night, it radiates into space, and we've been able to show that you can get about 15 degrees C cooling. So what would you do with this cooling? You could use it for air conditioning, you could use it for ice making, you could use it for refrigeration. And I think this is a new class of technologies that has been heretofore neglected, but could provide very valuable energy services in perhaps a much more efficient way than having to convert sunlight to electricity and then electricity to some kind of cooling. So just to now come back to the big picture, I said that what we needed to do is the rate of improvement in carbon intensity and energy intensity needs to be better than 5.5% per year, or minus 5.5% a year. And this isn't going to be easy. I think we all know this. But our common future under climate change depends upon it. And fortunately, we're in a situation where we have energy game changers. We have those that are here now: wind power, photovoltaics, natural gas. We have a suite of technologies that are coming soon, and we have a suite of energy technologies that are on the horizon. So with that, thank you very much, and we will move on to our next speaker. So thank you.
How do I get slides? They'll magically appear. Okay. Aha, they've magically appeared. Sally, thank you very much. Ladies and gentlemen, good afternoon. As Sally said, my name is Gardner Hill from BP. My role in BP is called Director of Carbon Solutions, and what that means is I look after or think about carbon and climate change as a risk to our business, and how do we address that risk, both at a group level as well as individual business levels. So we support our businesses think about carbon and climate change as a risk and how we manage that risk. As Sally also said, I've been involved in CCS for almost 15 years now, and time does pass quickly when you're having fun. And I think we have made some progress, but perhaps not as much as was thought when we started working on this 15 years ago. So what I'll do today is share with you some prospects or some thoughts on CCS, carbon capture and storage. And I'll start really by sharing the current status of CCS. I'll then look at the technologies and really the progress that's been made on technology. Then I'll cover why it's important. And importantly, then I should really cover costs. And is it too expensive or could it be cost competitive before I summarize at the very end. So green for forward. Okay, So the first slide is what is the current status? And so I really would like to acknowledge this slide I've taken from the GCCSI, the Global Institute for CCS, which really shows the progress that's been made on CCS over the last number of years. And so progress is being made. We have something like 22 large-scale integrated projects as defined by the GCCSI today. So these 22 projects are capturing around 40 million tons per year, which is not an insignificant amount of CO2. But importantly, 80% of that is being used for enhanced oil recovery, and that's primarily in the United States, where there's a very large industry of using CO2 to enhance the recoverable oil from the reservoirs. But importantly, 3 of these projects are based on power, which is the focus to really reduce emissions. And as Sally said, we have the Boundary Dam project in Canada, which is now operational, improving up the technology, particularly integration of that technology with the power kit. We have the Kemper County IGCC coming on stream probably next year, and of course the Petra Nova project, which is in construction. So I think there's a lot of progress being made on projects, and we're getting a lot of data to prove the technology does work. So the second slide shows my summary, really, of the status of technology. And I think the message I'd like to leave with you today is it's actually not a technology challenge. The technology is proven, both in these 22 projects, but also individually already in other aspects of the energy or power industry. So in the matter of capture, you can actually go out onto the market and get capture technology with guarantees from the equipment suppliers today. And that would be capture technology. It would work on natural gas processing, chemicals, and capture from power. On transportation, something like 6,500 kilometers of pipeline already exists that CO2 is being shipped on a daily basis. That's effective and safe transportation of CO2 is done now routinely. And on storage, CO2 is being injected and monitored in a number of ways. In oil reservoirs for EOR, something like 32 million tons per year of CO2 is being injected for EOR. And then in depleted gas reservoirs or deep saline formations, something like 8 million tons per year are being stored there. So there's a lot of experience and track record to say the technology is actually proven. That doesn't mean there aren't challenges to enable the broad deployment of CCS post the current demonstration phase. And so on this slide, I've tried to capture what I think are the main challenges still lying that need to be addressed for CCS. And the first one is the economics. So it simply costs more money to deploy CCS technology on an established process like power or indeed cement or steel. CCS is not economic today and hence requires something like a carbon price or some interim incentive to enable it to be deployed in the same way that most of the low-carbon technologies in the past were deployed. So wind and solar have all enjoyed the benefit of transitional incentives that have enabled them to come down that cost curve. Capital cost intensity is an additional challenge. Now, the interesting thing about CCS is it comes in large chunks. So when you apply it to a power station, that's the equivalent of many wind farms. And so each installation is a large installation, and that means the capital intensity is high. Even when you apply CCS to, say, smaller processes like some energy-intensive industries, even for that industry, it's additional costs, additional capital intensity. So that's another bridge, a hurdle that has to be jumped. And then the third one on the left-hand side is commercial complexity. Now, the reason commercial complexity is an issue is because along the CCS supply chain from capture, transportation, storage, there are a number of different players. And these players tend to have different levels of risk tolerance. And with different levels of risk tolerance requires different levels of remuneration to handle and manage that tolerance. And so that's part of the complexity. Also, when we look at the policies being put in place for CCS, there has been a great focus on applying CCS to power. And so you may incentivize the power producer to deploy CCS, but it's not clear what is the business case to build storage and to invest in storage and build transportation at the scale required for the broad-scale deployment post-demonstration. And then the third issue really is liability. How does liability for the CO2 captured, transported, and stored change along the value chain and between the parties involved? Turning to the right-hand side, technology. As I said, technology isn't the challenge. It's available today, but work needs to be done in technology to improve and reduce costs. It will improve reliability and, importantly, reduce the energy penalty of deploying CCS and to improve the integration of CCS with current processes. Now, I've singled out storage and transportation infrastructure as a specific hurdle. And again, that takes me back to the point that most of the focus so far has been in capture. But for wide-scale deployment, pre-investment is required in transportation, and particularly to make the storage capacity available. So how do you encourage commercial investment to make that storage capacity available, particularly when the time frame may require up to 10 years to appraise and develop suitable storage capacity? And then finally, public acceptance, the social angle. This can and has been a problem, particularly in Europe, when projects have been promoted and proposed to be onshore. Offshore probably is less sensitive and would certainly make sense in the UK and Europe. But certainly onshore is possible in areas that are less densely populated. So let me move now to the technology. This picture shows the sort of supply chain for CCS. So capture, we have pre-combustion, post-combustion, and oxy-firing. This tends to be the most expensive element in the chain, typically anything from 60 to well over 100, maybe $200 per ton at current costs. Transportation, again, pipelines and ships are the typical ways you can move CO2, and the cost is simply distance dependent. And then storage, you can use CO2 in enhanced oil recovery, store it in saline formations, in depleted reservoirs, or indeed even enhanced coal bed methane, which has been tried and proven. So let me talk a little bit about each of these technologies. Capture technologies are being proven, and much work has been done on R&D over the last 15 years. And much of that R&D, in fact, has delivered successful results. Pre-combustion, post-combustion, and oxy-firing have very different attributes and will find different applicability to different industries. This picture here actually shows the one-through steam generator, the OTSG, and the bottom right-hand side of the plot here shows the CO2 capture project logo. And this, in fact, was a demonstration project run by the CO2 capture project recently in North America. And this is an oxy-fired system. So technology is available today for natural gas, for coal-fired, for gas combustion sources. And the cost and energy requirements of CO2 capture are significant. So there's an energy penalty, and it can be something in the order of 20%. But the new technologies are looking to reduce that substantially. This is, again, the external picture for that demonstration. So that's the flue gas from the oxy-firing system. And this final picture shows the combustion of the oxy-firing in the burners, which is a mixture of pure oxygen and methane. So moving on to storage. Storage at large has additional challenges over the small-scale demos, primarily that have been done to date. So typically today we have pilot and demo scale, which is around about 100,000 to maybe 1 million tons per year of CO2. There have been some larger projects, and the Sleipner project is a larger project at around about 1 million tons per year, and that's now been operational for 20 years. So again, a substantial amount of learning has taken. But we need to move away from these smaller projects, these larger projects, for large deployment if the technology is to make a difference to climate change. And so we need to be thinking about ramping that up to between 10 and 100 million tons per year. So there's an order of magnitude scale involved here. The second issue is site characterization. And I'm now referring to the top right-hand part of this graph. Large amounts of baseline data are required for the formation, for the overburden, and the surface to understand and de-risk uncertainties with the storage site proposed. Oil and gas field exploration and appraisal is usually performed with a handful of wells to develop the site and generally covers a fairly limited geographical area. But for CO2 storage, we need to think about basin scale. So we're typically thinking about hundreds of wells and understanding the way to monitor basin scale requirements. So reservoir dynamics. While CO2 plumes are relatively small, perhaps order of tens of kilometers, the spatial extent of pressure could cover the entire basin, and that could be hundreds of kilometers. And so active management of this pressure-affected area is important. And indeed, some people are looking at brine extraction as a way of decreasing that area and simplifying the management of that. And the last point here is monitoring. Monitoring does need to cover these large spatial and also temporal scales. Continuous and automated approaches are needed with permanent and remote sensing, such as satellite and automated vehicles, could be used. Importantly, the combination of monitoring techniques proves increased accuracy and much reduced cost through things like inversion, which is really trying to mix together things like 3D seismic and, say, satellite, which is in fact represented by this lower left-hand picture. And we found that an effective way to do remote monitoring of CO2 storage sites. So let me move now on to why CCS is important. And I'd like to acknowledge this is an IEA figure. We heard from the IEA this morning. And what this tells us is that the IEA estimate that CCS could contribute up to 14% of the cumulative emission reductions between 2015 and 2050 compared with business as usual. Now, what this picture also shows is their anticipated ramp-up of the scale of CCS. And I'd like to draw your attention to the application of CCS, both in the OECD and the non-OECD countries. So on the right, it shows how the contribution, the build in the non-OECD countries is really quite important and dominates in the 2030 and 2050 timeframe as developing countries continue to improve their economy. But this figure also shows the flexibility and diversity of CCS. It shows that it is applicable not only to power, but to many energy-intensive industries, such as the petrochemical industry, cement and steel. So a lot of flexibility for CCS to contribute emission reductions in a number of energy-intensive industries. So that's why CCS is important. Can it be cost-effective? A number of analyses by the IEA, by the European Commission, by the ETI, the Energy Technology Institute, and the DOE in the US have all suggested that it costs more to meet climate targets if you don't have CCS available to play its part in the portfolio of technologies needed to reduce emissions. This graph is actually a new analysis by BP, and it shows the levelized cost of electricity in North America to 2050. Costs shown on the chart are the expected cases in 2010 US dollars in dollars per megawatt hour, and it also shows the 2050 numbers on the right. The orange and green cross-hatched bars show the effect of an $80 or $40 per ton CO2 price. And the pale green and yellow bars show the impact of integration, for example, for renewable power generation. This is a new analysis by BP, which we do periodically as part of our work on identifying long-term technology trends and views. And indeed, in November this year, BP will be issuing a new BP Technology Outlook, which is indeed our view on the development of long-term technologies. So it will address issues like batteries, CCS, and other emerging technologies that Sally mentioned earlier. But importantly, what this graph shows here is that comparing gas with CCS by 2050, it shows that it is highly competitive with other alternative and low-carbon technologies. I've also brought here a slide from the UK. So that one shows the US, but what about the UK? And this is an analysis carried out by the ETI, the Energy Technology Institute in the UK. And what they've done is try to estimate how CCS could deliver cost savings for the UK to meet its climate targets. And they've shown the potential cost savings in 2030, 2040, and 2050 by these subsequent bars. This is a peer-reviewed energy systems model. The UK estimates the CCS capacity to be 110 million tonnes per year of CO2 by 2050. This study acknowledges that CCS needs more fuel. It needs more site space and operational resources, but these clearly are far outweighed by the benefits in reducing the need for more expensive hybrid vehicles, for building retrofits, for alternative intermittent power capacity, and associated transmission costs. So they've done a detailed analysis and estimated these savings per year between 15 and 45 billion per year cost savings by 2030. So again, what's important to say here is this is not a panacea technology, but it's an important element of our portfolio needed to meet climate targets. So let me summarize. CCS is currently the only technology to enable large-scale use of fossil fuels in a highly carbon-limited world. CCS technology component parts are currently proven and used in industry and in a number of large integrated CCS projects. But CCS is not commercial today. It needs a real price for carbon and possibly some transitional incentives to really get down that learning curve in the short time frame needed. Industry collaboration and government funding are needed for CCS technology and to enable that wider deployment. What I thought I would do is finish on a slide to explain a little bit about what BP is doing, because this morning we heard from the IEA and others about the important role the energy industry has to play at the COP21 meeting and indeed in helping solve the climate change problem. As Sally mentioned, BP's been deeply involved in thinking about climate change for more than 15 years, investing in alternative energies and trying to improve the efficiency of the products we produce. So we are playing our part in addressing climate change by investing in natural gas and renewables as low-carbon sources of fuel and power. And we factor in a cost of carbon into the valuation of proposed projects, and we're advocating a global carbon price. And we heard the call for that earlier this morning. You may have seen that in May this year, our CEO, Bob Dudley, joined an unprecedented initiative with the leaders of British Gas, ENI, Royal Dutch Shell, Statoil, and Total, in jointly issuing a statement supporting a price on carbon and highlighting the potential role of natural gas in tackling climate change, and indeed could help to displace coal. So we believe it's about sustainability, it's about saving and switching. There's no silver bullet. We need action on many fronts, and we need a portfolio of technologies. But we need to incentivize energy efficiency. That's a really important aspect. We believe switching from high to low carbon is important, so moving from coal to natural gas. Incentivizing innovative new low carbon technologies so they become economic, like CCS. And we believe a price is important so the market can pick the winners. Ladies and gentlemen, thank you very much.
Okay, good. Is it good afternoon? Yeah, it is good afternoon. So I'll be even quicker than he was. We have plenty of time for discussion. So I'm Mark O'Malley, University College Dublin. I want to thank Sally for inviting me here, but I want to thank her as well for setting me up so nicely. She has said I'll say certain things, so I will. How do I move the slides on? Do I push the green button? Okay. Yeah, okay, that is the green button. Okay, so what I'll do is I'll try and explain what is energy systems integration, first of all, why it's important, and its role in the integration of renewables, which Sally mentioned earlier. And also, not that it's, it's one aspect of it that I think is very important, it's the importance of the consumer. I'm not a social scientist, I'm an engineer, so my perspective is from an engineering point of view. I think the consumer's role in this is incredibly important. So what is it? So it's systems thinking. It's to think of the entire system together. So there we go. So this is a slide that was developed at NREL, the National Renewable Energy Lab in the US, and it's trying to get the whole concept of energy systems integration across in one diagram. So along the left-hand side, we have single technology campuses and regions. Across the top, we have energy sources, and on the bottom, we have energy use. And, we have energy in the form of electricity, thermal fuels. Data is an enabler, which Sally mentioned. The ICT technology industry enables all this. And interesting enough, we think that water is part of this because water is a huge user of energy and it's also a huge enabler of energy. So we think water is also part of this. So what it is to optimize the energy system across multiple pathways and scales. So to optimize it, so to make electricity and heat and gas work better together to increase efficiency. And you'll see later on, I'll give some examples of that. Across scales, I mean, at the moment we have a situation whereby we use energy in our homes, but it's produced at these large power plants in the system that are distant from you. I'll give a simple example of where one side can help the other better if we can integrate it across the scales. So the sort of the metrics on which it should be measured is, it's not a single technology. We are technology neutral. I mean, Sally has went through a wide range of technologies, and my colleague has gone through one particular technology. We are technology neutral, but what we're trying to do is increase reliability, performance, minimize, and I've put in bold cost and environmental impacts because for this audience here, environmental impacts is probably the single most important thing. We're trying to make the system more efficient. I think I should point out, though, we're not trying to optimize it from an engineering point of view because we know that engineers will design a system that no one will use. So this is why I'm going to bring up the issue of the consumer. It has to be a system that people will actually use. It's most valuable at the interfaces where the coupling and interactions are strong and represent challenges or opportunities. So in many ways, when we put this slide up, people think we're going to do everything. We're not. We're simply, energy system integration is to concentrate on those places where these interactions are strong and they either cause a problem or there's an opportunity. So there's an opportunity for cost savings, emissions reductions, etc., or because of the interaction, there's a problem on the system that's causing increased costs or increased emissions. So that's the focus of it. The control variables, the things we work on, are technical, economic, and regulatory. So it's not just engineering. It's engineering, social science, economics, etc. So an example, and I'm not here to, because I reckon most of the people in this room are not electrical engineers, so I'm not going to explain this in full detail, but it's an example of energy systems integration. So effective load carrying capability is a reliability characteristic of a power system. That's all I'll say about it. And what we're showing here is that this is the ELCC of 700 megawatts of domestic electric heat storage under optimal operation. So this is the classic case of you have some sort of heat storage in your home, and we wanted to work out how does that contribute to the reliability of the entire power grid. So this is a case from your home right up to the power grid, which is this across scales. It's obviously heat and electricity together. It's enabled by data because the entire issue of trying to control electric storage heaters for the good of the grid is essentially a data issue. And the retirees and workers. So this is a characteristic I've plotted out here in green and yellow, and it shows you that for different types of consumers, their contribution to ELCC is different. So that's bringing in the consumer and society. So this is a case where a single technology in your home makes a contribution to the entire reliability of the entire power system. We can quantify it. So it's a very simple example. If people want to know more about it, I'll give it to them, but I don't want to get dug into the electrical engineering aspects of this. Water, again, I've mentioned this. I think, it's an incredibly important part of this entire. I'm not going to go into any huge detail, but some statistics. California, 19% electricity is used on water pumping. If you are desalination, etc., we're actually in Ireland, we're actually upgrading our water system. We're about to spend $7 billion on it, and we're going to do it in a way that makes it both efficient but also flexible from the point of view of the water system can interact with the energy system to give benefits for integrating renewables. I'll say no more about that for the moment. The international context, I mean, this is, if you look at the EU launched or did this integrated roadmap, the set plan, it sort of, it came out with a new version of it, so to speak, just before Christmas in December 2014 in Rome. If you look at that document and download it, if you look up integrated energy system, you'll find it everywhere. So Europe realizes that in order to do these things, to have a low carbon economy, you have to take an integrated approach to the whole system, both from a market point of view and a technical point of view. In the US, a good example of it is that NREL have recently opened a facility called the Energy Systems Integration Facility in Colorado. It's a $150 million investment in trying to promote these type of technologies. So let me try to get into the importance of it for integration of variable renewables. I don't know if people like this slide, some people don't, but I think it's a good graphical slide of what some people want to happen and what it is actually happening in some places. Particularly in Europe at the moment, this is essentially happening, is that renewables, low demand, are pushing coal and CCGT out of the system. And when you do that, you end up with a system with many more renewables. They are, as a technology, they have two aspects of them. There's a technological aspect and there's a resource aspect. I'm not going to talk about the technological aspect of integrating it because it's a very technical issue. And for an audience like this, I'd rather keep away from it. But from a resource point of view, what's happening is we're putting an awful lot of variable renewables onto the system, and how do you integrate them is the question. This is not one thing to say. It is essentially an electric-focused issue. But let's be clear about it. I mean, Sally mentioned electricity, sort of the CCS of electricity. Electricity is becoming much more important in the system because to decarbonize large-scale renewables, you have to go through electricity. Nuclear, whether you like it or not, I don't know, but you're not going to put a nuclear power generator in your house to heat your home. So electricity, and then on the demand side, Tesla, electric vehicles, etc. So there's no doubt about it, electrification is more and more important. But there's other aspects of the energy system that we shouldn't forget. But I'll concentrate on the electric part because it's what my expertise is in. This is not a new area. In fact, if you see in the top left-hand corner, elements of a new target model for European electricity markets, Paris 8th and 9th of July. The reason I was late is because I gave a talk there this morning. There's an entire conference going up across the river on how to design markets, basically to integrate renewables. So it's a very, very topical area at the moment. Down the bottom, the IEA have a task 25 that you can read about it, etc. So it's a very, very topical area. It's happening in all domains. The economists are looking at it, the social scientists are looking at it, the engineers are looking at it. So it's a very topical area at the moment. So just get some examples. I pulled some old slides together. I got these in 2011, and it shows you wind curtailment in China. So if you're going to build large amounts of renewables, China leads the world in terms of installed wind, and probably will soon lead the world in installed PV, I would suspect. But they have enormous problems in that they're curtailing it. They're throwing an awful lot of it away. Now, these statistics, it's difficult to get really good statistics out of China, but you can see that these numbers are enormous. I mean, 23%, 25%, these are huge amounts of curtailment. So you're building wind and or solar, if you want to take a solar case, and you're actually dumping the energy from a CO2 point of view, this is not a good idea. And the problem arises because of integration issues, which I'll talk about. To update it, I went and looked for more data, 2013. These are official statistics, which may not be, officially the Chinese may not be willing to accept how much curtailment they have, but it's still pretty high. So why is this happening? Before I go on, so it's happening for many reasons. They are, largely speaking, integration related. They don't have the proper market signals, they don't have the proper transmission, etc. So they are all in this basket of energy system integration. But I just want to pick on one particular example of it that I've worked on with my colleagues in Tsinghua University. One of the reasons they're curtailing wind in certain regions of China is because they have an awful lot of combined heat and power. Combined heat and power tends to be extremely inflexible, and the heat demand drives everything. So you have a situation whereby, and you're not going to turn down the heat because human beings may die because of the heat or because they're cold. So what's happening is essentially it's not the only reason the curtailment's happening in China, but it's one of them, is that the wind has actually been turned down because the CHP is on to produce the heat and it has electricity and you have to take it. And in good old power system engineering terms, you have to keep the system in balance, otherwise it blacks out. So we looked at various ways of improving this. So the much darker area in the three diagrams is the current existing operational range for heat and electricity in CHP. The lightly shaded area is how we can improve that or increase it by installation of electric boilers, installation of heat storage, or a combination of the two. Essentially, we're making the CHP more flexible. Now, there's costs associated with that, and I'm not going to dwell on it. I mean, it's costly to do it, but you can see the effect in the next diagram. If you look at it business as usual, if we leave it as it is, the electric boiler, the heat storage, or a combination of the two. And just to point out, the brown wind curtailment, as you can see in the business as usual, is larger than in the other three. So you can see that by making the heat system in the combined heat and power more flexible, you integrate more renewables, and it helps reduce CO2, etc. So that's a very good example of it. The picture on the right is a very good friend of mine called Charlie Smith, and I don't know if he coined the phrase, but if you love wind or solar, you have to at least like transmission. I'm not here to talk about electrical transmission. I'm here to use this as a vehicle to raise the issue of the consumer. But very simply put, if you wish to integrate large amounts of renewables, and I'm not saying it's the only way to do it, but certainly the cheapest way at the moment to do it is to build large amounts of electrical transmission. I realize that there's issues around that, etc., but it is the most cost-effective way of integrating large amounts of renewables. There is no competitor for it in comparison with cost. Now, the economists in the other conference are just pure out-and-out economists. I'm an engineer. There's always a middle ground. But this shows an example of how renewable or how transmission can help smoothen out the solar profile. And one of the problems we have, if the profile is very sort of noisy, etc., it makes it much more difficult to integrate. So it smooths it out and it helps us integrate it. But like I said, I'm not here to specifically talk about transmission. I'm here to introduce the consumer. The problem with building transmission is, and these are various, just images I got from various places, is that in large parts, particularly the Western world, consumers do not like transmission. In fact, the one on the bottom left is actually a protest about building transmission for a coal plant. I'll have to admit that. So they're trying to stop the coal plant. But there is huge public opposition to the building of transmission and, in fact, wind turbines and infrastructure as such. So they play an enormously important role in this entire thing. Like I said at the start, engineers, we will produce the most optimal engineering solution that you could ever see. But whether society will accept it is incredibly important. So this is a recent paper in Nature. Engineering economists are ignoring people and miscasting decision-making and action. And in fact, prior to that, in previous slides, I had a friend of mine from Durham University used to say essentially the same thing, but this guy got it published in Nature, so I told him, you should say these things, you should maybe send them to Nature. But the point is clear, that consumer behavior and integrated energy system is very important. So my own take on it is that people talk about the so-called trilemma, which is competitiveness, sustainability, security, supply. I actually think it's a trilemma plus the consumer. I think the consumer is the fourth element of this. To give you another example of where the consumer and technology together may be able to help, a lot of people ask the question about what about 100% wind, 100% solar. This is one of the questions people ask. There's some extremely good studies on it. Like, for example, it's the REF study in the US that went to 80%. There's some really good work been done on it. But just as an illustration, and it's a very, it's a very crude illustration, but I think it makes a very good point. This is the Irish electricity system currently gets 20% of electricity from wind. We're going to 40%. This is 2010 wind profile on a monthly basis. It's not on an hourly basis. I could do it on an hourly basis, but just on a monthly basis, and our load on a monthly basis. But the wind is scaled up from 2010, so the energy is the same. So the area under the curve is identical. If Sally mentioned demand-side management, mentioned storage, etc. If you look at the difference between the blue and the red curve in the middle, essentially this is the missing gap. This is the amount of energy that you may have to store across the seasons, okay? I can assure you there is not enough batteries, there's not enough materials in the world to store this amount of energy. So it's not even can they make it cost effective? There just isn't enough lithium, etc. It's just an enormous amount. So you're never going to solve this problem. Now I realize it's a very extreme case, but nonetheless. So, and the picture of the guy with the microphone saying, spilling wind. You could overbuild the renewables to an extent that you dump an enormous amount of it, but the economics are not great. So maybe, and this is my proposition to people, maybe we should society should learn to, and the technology should be developed so that society lives its life according to how the energy is available. So for example, in this curve here, for Ireland as it turns out, high energy intensive industries maybe should operate during the winter. Maybe you should have manufacturing processes that have high energy processes during the winter, because that's when we have a lot of wind. But maybe the same equipment, the technology can be used to make lower intense energy devices during the summer. That's just my take on it. So that's a technological issue, but it's also a societal issue combined. And that's just my sort of way out there type of proposition. So keep calm and love social science. So just policy failures then, I mean, because it's about policy as well. I just came from a talk with a bunch of economists, and my parting comment on them wasn't very, we didn't get on too well, I'm afraid. Economists just look at money. That's all they look at. Engineers just look at technology, and we're both wrong. Somewhere in between is the middle ground. I think the consumer is the other part of that. But let's look at some policy failures. This is a Bloomberg, it's off the web, it's a couple of years old. Windmills overload East European grid, risking blackout in energy. This can be traced back to, this report has the details, but this can be traced back to the inability of policymakers to take on some very basic scientific advice from engineers and economists how to operate electricity markets. And for some reason in Europe, they simply will not do it. They do it in the United States, but they do not do it in Europe. And because of it, we've actually reduced the reliability of the power system. The entire electricity industry in Europe is in crisis. And that's what that conference was up the road. And mainly it's because people didn't take a holistic view. You take the physics, you take the economics, you take society, and you work out a pragmatic solution that is consistent. And unfortunately, that's typically what not happens with policymakers, because they're typically looking at the next 4 years, etc. So that's my dig at the policymakers. So this institute that Sally mentioned earlier, so a group of us around the world believe that this whole issue of the whole entire energy system being integrated properly together is very important. We formed this institute called the International Institute for Energy System Integration. The founding members are on the bottom, but now there's more people involved in that. This is a recent, you can download this on the web. So we held a meeting in London in Imperial College. I don't know if you can see in bold there, we say, need to combine economic, social and political perspectives with engineering knowledge. So we believe that the research questions here are definitely multidisciplinary, etc. This organization has had many events. The next event it's going to have is actually in the IEEE meeting in Denver. And we have a PhD course running in Denver as well. And we have a meeting then in Korea. So we've met in Japan, we've met in Washington, we've met in Denmark. So we're pretty active. And I think we're going to have a meeting in Stanford probably in 2016. So, conclusions. It's more about the whole integrated energy system than ever before. Energy system, it can reduce costs, increase penetration of variable renewables. It can have benefits. So it's not a single technology. It's just how you put them together. And if you, in this area at the moment, it's, you know, everybody asks about it. They all talk about the integration of things. And if you do it wrong, you get curtailment of wind, for example, et cetera, et cetera, et cetera. It's definitely multidisciplinary, and I definitely believe the consumer is a central part of it. I think that's it. If I can push the slides on. There you go. So a lot of the slides I've used are from my colleagues. I've given up trying to label each slide because I forget, but I get them from my colleagues around the world, so I'd like to thank them for their slides. Thank you.
Are these on? Okay, terrific. Well, thank you guys both very much for setting the stage for what I hope will be a lively discussion. I think to kick it off, I'm going to ask a couple questions. So your work isn't quite done yet. So I want to talk about CCS. I've been involved in CCS now for about the same amount of time as you've been involved. And I'm really feeling like CCS is facing a lot of headwinds right now. You know, we hear it's just too expensive. We hear the public doesn't like it, which is, you know, largely true. It's not a preferred technology. We hear it just won't be ready in time, that it'll be too late to really make a difference. So that's sort of the headwinds. And then over the last day and a half, I was reminded about how important CCS is, both with regards to dealing with the emission sources we have today, and then as the potential to combine it with biomass energy for BECCS. So how do you think about this? How do you reconcile, you know, these two completely different sort of views about where CCS and its importance?
Is it on? Yeah. Okay. No, I think Sally, you've actually painted the picture as I see it. I think there's a real dichotomy. On one hand, a number of analyses from the IPCC, IEA all say CCS has a very important role to play to hit these climate targets. But on the other hand, at a country or regional level, we're finding it very difficult to get into action. It has been 15 years, and I guess if I was sort of saying the glass is half full, you could say, well, we have 22 projects, we have a number of integrated projects, we now have 3 in power, so we now have some sort of foundation which should give us confidence to move forward more quickly than we have in the past. But what's still missing, I think, is that commercial framework, is the price on carbon or the transitional incentives that will enable people to make commercial investments to deploy the technology at scale. So really the question is, how do you now move from the demonstration phase to the wide-scale deployment phase? And I think there are 2 issues. Not only is there this commercial framework issue, but I think there's also a time frame, an important time frame element here. And that perhaps what's not widely known or understood is how long it takes to invest and to make that possible. So you can't actually wait until 2030 and say, well, let's flick a switch and have CCS now. You do have to pre-invest on transportation, pipelines. They take time to design and build. But more importantly, you actually have to do the appraisal and evaluation of suitable storage sites, whether it's oil and gas reservoirs or deep sealing formations. And they can take 5 to 10 years to appraise and evaluate to give you the confidence to actually then go and capture CO2. So there's a time scale element to this that perhaps maybe many governments or policymakers don't fully appreciate. And we need to perhaps be clearer in describing what that framework is. But there's a real dichotomy, and I think the danger is the longer we leave it, the window starts to close on the opportunity for CCS.
I guess I would question that the idea that the opportunity for CCS, I mean, I would love to be such a technological optimist that I would say in 2040 that there wouldn't be a need for CCS because all these other things had filled its place. I imagine, and many projections suggest that we're going to be using a significant amount of fossil fuels, long into the future. And if we're going to achieve a 2 degrees C target, we'll need it even more in 2040 or 2030 than we do now. So.
I think that's right. I think if you're absolutely committed to that target, then all the evidence we've seen today suggests you do need to deploy this at substantial scale, and you would need that more in 2040 than you do today. I think the other issue I didn't touch on, which is an important issue, is the public acceptance issue. And in Europe, that's perhaps been more critical than perhaps in other areas because the general population density is much higher. And there have been 1 or 2 projects that have raised particular public concerns, which certainly gave CCS a very negative public perception in the early phases. I think the current view in Europe is that if we're doing CCS, it would be pragmatic to go offshore, where there's a very established oil and gas industry, and do it there and build on the experience success of oil and gas, and that will be less of a public concern issue. That may build confidence and enable perhaps subsequent onshore activity at a later date. But clearly it is being done onshore in the US and other areas, but you really have to manage the public acceptance issue carefully. You shouldn't take it for granted. You have to show the co-benefit to the societal good and the local society as well as to the project.
Okay, thanks. I want to go back to this issue about the time frame. So I talked about 3 game changers that are, here now. And I think one of the challenges is from a public perception, these technologies appear to have emerged very quickly because they become visible once they really start to move up that scaling ladder. But if you look at the realities, those were technologies that significant government investment in the 1970s, sustained industrial and government investment, for several decades. And so then because of all that hard work, all of a sudden, in the 2000s, we see it take off. And so sort of trying to make an analogy with CCS, it was really in, I think, 1995, and it was Statoil with CCS that began to start that. So if we look at that, we're sort of 20 years into the process of development of a technology. So, and certainly I can say that in the 1970s and 1980s, everyone was saying, oh, solar PV will always be too expensive and wind will always be too expensive. They'll never be here. But look what's happened, you know, and I think similarly with battery electric vehicles, I think that there was a lot of skepticism that within the next 10 years or so that they could actually be cost competitive. But there are many companies suggesting that in fact that will be the truth.
Because I think that's an important point. But again, I think what I try to do is create a distinction between unit size and investment of solar panels and windmills compared to, say, a CCS. As I said earlier, they are really chunky. And it's easier for governments to put incentives on small units as opposed to one or two very large units. It's like almost placing big bets as opposed to small bets. But the problem is, if you do lots and lots and lots of small bets, actually the cost adds up, and it ends up being more expensive than if you had done one or two big bets. And I think that's part of the challenge.
Yeah, no, I agree. And I think that nuclear power, at least in the United States, is really suffering from that. Just the capital investment and the time between you start that investment and you start recovering on those, it's really, really a heavy lift. So Mark, maybe we'll jump over to you for a minute. And of course, you can jump in anytime you want. So one of the questions that people, I think, often have is, well, just how much renewable energy can we integrate into an electric grid? And of course, there's no single answer to that, but of course, I'll ask that question. And I'm going to ask you to think about it in two contexts. The first context would be for Ireland or Europe, you know, someplace where you've got a very mature electrical grid, lots of transmission, and so forth. And the second context would be in the developing world, where many of us have hopes that these countries can leapfrog, you know, the approach we took to developing our electricity systems. And what's involved in, you know, getting a high fraction of renewables available in countries where you don't already have a very robust grid? What are some of the integration options that would allow us to do that? So two questions in one.
Turns on itself. Very smart. Okay, so before I answer those questions, I just want to make a comment about what you're talking about, and I don't want to pick on CCS or nuclear or anything like that, but there does come a stage whereby certain technologies win out, and from a research point of view, we should maybe concentrate the money on some others. So, and I'll say that about the renewables. I mean, renewables have many forms. You know, there's wind, solar, there's ocean, etc. And some of them are just not going to make it in comparison. So there does come a time that, from a research point of view, they're lovely to think about, but their day is, you know, they lost their opportunity and they should be cut. So that's just a general comment to make. There is no limit. It's a matter of economics and societal, you know, how much do you want and how much you're willing to pay for. I mean, if you want numbers that make sense, we're going to 40%. We're an isolated system. It's cost effective. Well, sorry, cost effective when you want to make a certain target, etc. If you just talk to the pure economists, none of this is cost effective. But you can make it to 40 or 50% pretty easily, I'd say. But if you want to go further than that, you do have to take this much more whole energy systems perspective, because if you want to integrate very large amounts, if you look at Denmark are trying to make it to 100%, and what they are looking at is the whole issue about electricity and gas all working together in one system. Now, they have the great advantage that they are connected to a huge gas infrastructure in Europe and a huge electricity system, etc. But nonetheless, there is no limit. If you go to 100%, and that's why I put up that slide about 100%, if you want to go to 100%, you do have to change fundamentally the way you live your life, because I just don't think there's enough technology to do it. There is a very technological issue that I didn't mention in the background as well that will cause a lot of trouble for us, but this is not the audience to talk about it with, but there's some technological issues as well. So you can go as far as you want, 30, 40, 50%, I don't think it's a major problem. After that, you have to really think about the whole system, and to go to 100%, you have to really think about how you live your lives. The developing world, one of the problems we have in the Western world, so to speak, is that engineers have done an amazing job of producing electricity. It's the most reliable thing that you ever were served. It's much more reliable than the phone system, isn't it? Never end. We've created a problem. It's far too reliable. The electricity system never fails you, does it? Ever. And if it does, there's political problems. So in many ways, in hindsight, we produce a system that is so good that it's very difficult to backtrack from that. And that's one. If we were willing to accept, lower levels of reliability, you can cost-effectively go even further. But society will not allow us to do that. But in the developing world, where they do not have a reliable system, I think maybe the way forward is to make sure they develop in a way that develop a reliability of a system that's suitable for these technologies. So I think they can actually go further than us, but not at the same level of reliability. But they don't have any level of reliability in some places now. So I think it's a matter of doing it at a reduced level of reliability. The technologies, storage is one technology. It's still too expensive, but the incremental value that people in the developing world put on energy is enormous. They'll walk 10 kilometers to charge a phone. So storage probably makes sense in certain aspects there because the incremental value they put on it is so high.
Okay, thanks. So what we're going to do now is we're going to open this to the audience, and I was told that there would be someone to help us with the mics. Okay, yeah, we've got some mics out in the audience. So if you could just hand it to people that you see with their hands up, that would be great.
Thank you. Okay. Is that just me?
My name is Shunsuke Mori from Japan. Is that? Oh. I'm not so far.
After you, please.
Okay, please.
Okay, ladies first. Okay.
Thank you. My name's Emily. I'm from the University of Sussex in the UK. Sally, you mentioned right at the very beginning, one of the key things that we should be aiming for is reducing reliance on depletable resources. Now, I didn't so much want to talk about rare earths and lithium and stuff, but if any of you want to comment on that, then please do. But the thing with CCS, we're all aware of the penalty you get with CCS, the fact that it reduces the efficiency of the plant, which means that you then have to use more fossil fuels. Now, personally, I don't think that reducing reliance on fossil fuels is actually an issue because I think we've got too many fossil fuels out there rather than too few. But what we really need to decide is whether or not we actually do want to reduce reliance on fossils because they're depletable. And if so, then what are the implications of this for CCS? And it would be great if all three of you could comment on that.
Sure, yeah. One thing, I always live like 50 or 100 years in the future, so I know that sometimes when I say things taken in the short-term context, it's like, well, what? Why'd you say that? So I agree, in the short term, there's no real issue about availability of fossil fuels, and your point that maybe we have too many of them is a very good point. But looking to the long-term future, at some point it's going to get more and more difficult to get fossil fuels. We're going to have to go to remoter and remoter areas to get those. Some of those will be in pristine ecosystems that perhaps the ecosystem values of those won't justify interfering in those few places that humans have yet to tread. So I think that's a very long-term perspective. Yeah.
CCS.
No, the moving away from depletable resources. For CCS, I personally think if there are places where it makes sense now, so for example, if you have an ethanol plant, it emits nearly a pure stream of CO2. On the 1 million tons per year kind of scale. It's very low cost to capture that carbon dioxide and sequester it. There are some other good examples associated with refining and so forth. So I think that those areas where you don't have to spend a lot of money on capture are early win opportunities that we should pursue right away.
Name is Shunsuke Mori from Japan. I'm an engineering people. I have one comment and one question. One comment is to the first presenter. I think the game changer requires game supporters. In this, I'm talking about the infrastructure development and very sophisticated energy management system. And through the software side, probably we need a new funding system to encourage the consumers to investment, new equipment, and new systems, electric vehicles, and new high energy efficiency equipment penetration will also be the case. And one question is about to always about the future possibility of nuclear power. Today, we didn't talk about the future nuclear power. I understand the risk of nuclear power, but at the same moment, we will have to talk about the risk with nuclear power and the risk without nuclear power, especially under low-carbon societies. We have experienced a very serious accident, but if we can prepare the full technologies against possible nuclear power accident stations, probably future technological possibilities for nuclear power would contribute to the low-carbon societies. I would have the opinion. How do you think about the future possibility of nuclear power and the risk and benefit of nuclear power? Thanks.
Do you want to respond to the first part? Yeah, or whatever.
Well, the first part was really a comment, but yeah, I'll respond to the first part as well, to some extent. And correct me if I'm wrong, but you were sort of saying that we need to invest in new energy management systems and more IT technology. I mean, this might sound a bit sort of negative, but I mean, the IT industry, and we do need IT in this industry and we use it, etc., but its ability to change, without it we could make these things work, but its ability to improve on itself is actually quite limited, you know. So we can get a new energy management system, it gets a little bit of a tweak. So it's needed, but I don't think it itself is actually, I don't think it's, you know, as important, for example, as making CCS, you know, viable, etc., So I don't think its role is that big. In terms of nuclear, though, and from a systems integration point of view, because I'm technology neutral, nuclear power is very inflexible. So from the point of view of a system perspective, and you know, again, it's sort of like you have to design the whole. It's a systematic approach to say, if I want a low carbon society, then you find that if you have to have renewables, you then also find you have to have other flexible plant, and all of a sudden you end up with renewables and gas. And you don't have nuclear. So I think from a flexibility point of view, nuclear is not great. So the economics might be different, but from that point of view. And unfortunately, CCS is not great either, because my understanding, and correct me if I'm wrong, is that CCS is not that flexible either. Just as another thing though, just to show that I'm not biased in any way towards any technology, storage is a very important technology from a flexibility point of view. It'd be great to have it from an integration renewables point of view. However, it has one huge problem. Forget about its cost. It's got a round-trip efficiency loss, just like CCS. And so it's very difficult to justify the economics of both of them, because this lady said it consumes more fossil fuels. Storage, second law of thermodynamics, there's nothing you can do about it. What goes in does not come out. So I think that from a systems point of view, every technology has strengths and weaknesses, and there's certain combinations that work and certain combinations that do not. So I think the future, in my opinion, is from a low carbon point of view, if that's what you want, because I'm technology neutral, it's wind, solar, gas. Oh, and transmission.
Okay, let's take two questions maybe at once, and those will be the last two. Yeah, please over here. Yeah.
Andy Revkin, Pace University, New York Times. Great discussion. One thing that I see sort of consistently underplayed is the need for more science. I know it's always seen as kind of like, well, yeah, of course. But when you look at budgets across the OECD, and I've written about this for 10 years, the gap between what's stated about how much we care about mitigating climate change and what we invest in the basic RD&D end of it is huge compared to other things like healthcare, defense. So do you guys agree, first of all, and secondly, how would you make the case, an actionable case for doing it when, as Michael Grubb just said a little while ago, consumers are already getting electrons. It's not like it's there, it's a challenge. And the last part of this is about Michael Dove and Dan Kamen wrote a great paper almost 20 years ago on what they called mundane science, meaning like village scale, distributed power, and frontier science. So I don't know if you have your own sense of the importance of pursuing both of those. Thank you.
Okay, we'll take the one more question and then we'll answer them both at the same time.
Hello, my name is Jesper Teilgaard. I'm Chief Methodologist at Danish National TV. I think we need a couple of comments on shale gas, which mentioned by Sally. It's very huge in the US and maybe huge otherwhere else, but it is still fossil fuel. And I want to know if you can comment on, you think it will be a stepstone towards more renewables, or it will be a part of the system for many years, which I think it will, because now it is invented. But it is still fossil fuel, and it will make emission. And you all know that there are problems in environmental sources, maybe emission of methane and so on.
Okay, so maybe I'll take a stab at the R&D one first, and then others can chime in, and then we'll talk about the shale gas. So I absolutely agree that R&D is incredibly important, or science, as you called it. My personal view is that given how quickly the energy field is evolving, that we need to carefully reassess what is the appropriate role for academic research, industry research, and say national lab research. And it's my personal view that where we really have the biggest deficits are the technologies that are on the horizon, that there are many promising ideas, but they're nowhere close to fruition, and we can't afford to wait for 30 or 40 years for those to develop. So I think that's where we should really focus our government supported R&D, particularly at academic organizations and national labs. I think that industry is doing a fabulous job in, continuing to improve PV, now batteries, wind, and so forth. So I personally see less of a need in those areas than the on the horizon kind of options. Would you guys like to comment?
Yeah, no, I think R&D in science is hugely important, and it's certainly something that BP has been deeply involved in, because we believe that we need to make decisions based on good, sound science. I would say from 3 dimensions it's important. One is that the more science and education we do on climate and energy technology is good at informing the next generation of our society about the importance of climate change and energy technology. And I think the more we can get society understanding the challenges and issues, the more chance we have of governments getting into action. And we heard that this morning. That's the first one. The second one is that it will clearly drive down costs and improve innovation. And I think we've got massive gains to make in energy efficiency. One of the earlier questions was, what about the energy penalty of things like CCS? Well, the energy penalty of CCS is actually small compared to the improvements the energy system has made over the last 50 years. And in probably the improvements we can make in the energy system over the next 20 or 30 years. So innovation, I think, will take care of that. But you need the R&D and the science to underpin that. The third one, where I think R&D and science is important, is in knowledge sharing. I think time is short. But if you have integrated and collaboration in the science and R&D, you can share that knowledge and accelerate the pace of innovation and indeed bring us down that learning curve even faster.
On the funding of science, so I'll just tell a little anecdote. I served on the European Research Council engineering panel for several years. It's the most high prestigious grants that Europe gives out. And it was the engineering panel, so we dealt with all aspects. And we were very disappointed at the quality of the proposals we got in on energy. And the reason, I put it down to as follows: if you look historically, I don't know if this is true globally, but certainly from my own point of view and where I know well, energy research has not been that well funded in comparison with medicine and ICT, for example. And therefore the people with the skills are just not there. So they're very bright people, but they don't have the right directions. There's actually an enormous mentorship problem going on. There's not enough senior people with really good experience, because the problems with a lot of proposals we got in was that they were beautiful scientifically, but they were asking the completely wrong questions. So there was a complete dearth of knowledge in the whole area. So I think there needs to be more research money in it, but we need to make sure we build a human capital that can actually ask the right questions. In terms of the mundane, I think I heard mundane and basic. And maybe, again, don't get me wrong, I mean, I think the mundane part is actually the social science. I don't mean it's mundane. I mean that it's actually what human beings will actually do, to understand that. And that's really good social science research. So I would say we need to put more money into social science. And in fact, if there's only a cap on the budget, and this is where I get into real trouble with my colleagues, I believe there's far too many people doing engineering research that's of no use to anyone because it's misdirected, and I'd rather put that money into social science.
Okay, and I'm going to take the prerogative as chair to have the last word. I want to address the issue of shale gas. I think that shale gas can be done right, and I think shale gas or natural gas in general can be done poorly. If we have the appropriate policies in place, we can utilize the capacity of natural gas for flexible generation to increase the penetration of renewables. But if we neglect the opportunity, I mean, for example, if natural gas just starts pushing renewables out of the way, I think that's a real problem. So there needs to be policy measures to assure that doesn't happen. With regard to leakage, we've done a lot of work on leakage. 2 of the U.S. experts on leakage are at my organization. What we found is that there is more leakage than the EPA thought there was. But what we found is that the leakage is very spiky, meaning that there are a very small number of very large sources. And there's a lot of work on detection of those sources. And what we're finding is that they tend to be things that are easily fixed. For example, valves left open and so forth. So I believe that that's a solvable problem. With regard to the subsurface impacts, what's been found through extensive study is that there is little groundwater contamination associated with shale gas that has to do with wells leaking and hydraulic fracturing per se. In those regions where there are impacts, they tend to be associated with improper surface water management and disposal. And more you're seeing drilling operations such that all of the drilling fluids are contained in containers and disposed of more carefully. But again, that's an area where more work is needed to assure that natural gas gets done right. So those are my views on that topic. Anyway, well, thank you all for staying. I thank the panelists and speakers. I thought you did a wonderful job, and thank you.